Welcome back. In this video, we are going to learn about physical and thermodynamic properties of moist air, which is the natural and actual form of air that we all are surrounded by, which is composed of water vapor or steam and dry air, which is also a mixture of nitrogen, oxygen, carbon dioxide, and other such gases. In other words, moist air is a mixture of both dry air and water vapor, which are non-reacting. These properties that we are going to learn about are humidity ratio or specific humidity, as both terms are used interchangeably in engineering, where dry bulb temperature of the moist air does not vary significantly, and relative humidity. And finally, we are going to learn to derive their mathematical expressions using fundamental principles. Since dry bulb temperature, relative humidity, and specific humidity are independent properties of moist air, meaning variation in any one property does not cause automatic change in other properties. In other words, any one property can independently be varied without depending on other properties. Any two of them define the thermodynamic state of moist air on the psychrometric chart or diagram, meaning two independent thermodynamic properties of moist air apart from the given pressure are needed to get the state of the moist air fixed on the psychrometric chart according to Gibbs phase rule, and this helps in determining other thermodynamic properties of moist air, which is drawn for moist air at a particular pressure, usually atmospheric pressure, between its dry bulb temperature, horizontal axis, and its specific humidity, vertical axis, with exponentially curved, non-parallel, divergent rightward relative humidity lines that lie on psychrometric chart, because saturation pressure of the water vapor rises exponentially with temperature, that is dry bulb temperature. Since we are going to use this question as a learning reference, which is from GATE 2013 MESET A, let's first read out this question and try to analyze and understand it for what is given and what is asked. The pressure, dry bulb temperature, and relative humidity of air in a room are 1 bar, 30 degrees Celsius, and 70% respectively. If the saturated steam pressure at 30 degrees Celsius is 4.25 kilopascal, the specific humidity of the room air in kg water vapor per kg dry air is. Alright, so this question is asking about the specific humidity of moist air in the room. Alright, and to find the specific humidity of moist air in the room using its mathematical expression, we need partial pressure of water vapor of moist air in the room at the dry bulb temperature, and this partial pressure of water vapor can be determined using the mathematical expression of the relative humidity. So, from the given information, the pressure, which means the total pressure of air, which is actually moist air in a room, is 1 bar. Alright, therefore, the sum of the partial pressures of dry air and water vapor is given by this expression. Alright, according to Dalton's law of partial pressures, which says that the sum of the partial pressures of the individual gases, which must be non-reacting in a mixture, is equal to the total pressure of the mixture of the gases. The dry bulb temperature of air, that is moist air, which is actually the temperature of the moist air as measured by a simple thermometer in a room, is 30 degrees Celsius. So both the dry air and water vapor in the room are at this dry bulb temperature. The relative humidity of air, that is moisture, in a room is 70% or 0.70 in decimal form, where relative humidity is defined as the mass of water vapor that the air, that is moisture, in the room actually holds at a given dry bulb temperature of TdV divided by the maximum mass of the water vapor that the same moist air in the room can hold without condensation at the same dry bulb temperature of TdV. Alright, so mathematically the relative humidity is given by the following expression. Alright, so we have the mathematical expression of the relative humidity, which is given by this equation 1. Since we generally assume that both dry air and water vapor are ideal gases, moist air behaves like an ideal gas too, because we know that the mixture of two ideal gases also becomes an ideal gas. Now we are going to write the ideal gas equation for the water vapor component of moisture with a partial pressure of PV, volume of V, which is also the total volume of moist air and remains the same for both the water vapor and dry air, as both occupy the same total volume of the moist air. Mass of MB, characteristic gas constant of RB, and temperature of TdV, which is the dry bulb temperature at which the moist air and its contents exist. So, mathematically, the ideal gas equation for the water vapor is given by the following expression. Alright, so we have the ideal gas equation, which is applied to the water vapor, which is the component of the moisture in a room. Alright, now we will rearrange this equation to find the expression of MB. Alright, so we will rearrange this equation to find the expression of MB. Alright. Alright, after rearranging this equation, alright, we have the expression of MB, which is the mass of the water vapor in the moist air. Similarly, we are going to write the ideal gas equation for the water vapor component of moist air in a room when the moist air becomes completely saturated and holds maximum amount of water vapor with mass of mb max at partial pressure of pbs, which is the saturation pressure of water vapor at the dry bulb temperature. Volume of V, characteristic gas constant of RV, and temperature of TdV. So, mathematically, the ideal gas equation for the water vapor when moist air becomes saturated with water vapor is given by the following expression. So, we have the ideal gas equation applied to the water vapor when the moisture becomes saturated completely. Alright, so what this ideal gas equation for the water vapor represents is that when moisture holds maximum amount of water vapor at a given dry bulb temperature, the partial pressure of water vapor becomes the saturation pressure of the water vapor or steam at the same dry bulb temperature. Alright, now we will rearrange this equation to find the expression of mb max. So after rearranging this equation, we have the expression of maximum mass of the water vapor that the moist air in the room can hold at the given dry bulb temperature. Alright, and this expression is given by the equation 3. Alright, also we are going to write the ideal gas equation for the dry air component of moist air in a room with a partial pressure of Pa, volume of P, mass of Ma, characteristic gas constant of Ra, and temperature of TdV. Now, let's move to the next page. So, mathematically, the ideal gas equation for the dry air is given by the following expression. Right, so we have applied the ideal gas equation to the dry air component of the moisture in the room. Now, we will rearrange this equation to find the expression of Ma. Alright, so after rearranging this equation, we have the expression of Ma, which is the mass of the dry air in the room, and it's given by this equation 4. Now we will plug in the expressions of mv and mv max from the equation 2 and equation 3 respectively into the equation 1. Alright, now we will simplify this expression. Now we will rearrange this expression to find the expression of PV. So after rearranging this expression, we got the expression of PV, which is given by this equation number 5. Since the value of RH is 0.70 and that of PBS is 4.25 kilopascal, which is the saturation pressure of steam or water vapor at the dry bulb temperature of 30 degrees Celsius. If PVS, that is partial pressure of water vapor in a saturated condition, but not given, then we would just have to obtain its value from the saturation steam table for the temperature. Alright, we will plug in the values of RH and PVS along with their units in the equation 5. So after plugging in the values of RH and PVS, we have this expression. Alright, now we will simplify the calculation of this expression and solve for the value of PV. Alright, so after simplifying the calculation, we have the value of the partial pressure of the water vapor of the moisture in the room. Specific humidity omega is defined as the mass of water vapor md that the air, that is moisture in the room, actually holds at a given dry bulb temperature of TDV divided by the mass of the dry air Ma that the same air in the room actually has at the same dry bulb temperature of TDV. Alright, so mathematically specific humidity omega is given by the following expression. So we have the mathematical expression of the specific humidity. Alright, now we will plug in the expressions of MB and MA from the equation 2 and equation 4 respectively into equation 6. Alright. After plugging in the expressions of MB and MA from the equation 2 and 4 respectively, we got this expression of the specific humidity. Alright. Now we will simplify this expression and rearrange it in a more simplified form. Alright, so after rearranging this expression and simplifying it, we got the more simplified form of the specific humidity expression. Right, and we are going to assign it equation number 7. Alright, now let's move to the next page. Since the value of Ra, which is the characteristic gas constant of dry air, which is obtained by dividing universal gas constant by the molar mass of the dry air, is 287.042 joule per kg Kelvin, and that of Rv is 461.524 joule per kg Kelvin, where Rv is the characteristic gas constant of water vapor, which is defined as universal gas constant divided by the molar mass of the water vapor. Alright, we will plug in the values of Ra and Rv along with their units in the equation 7. Alright, alright. So after plugging in the values of Ra and Rb, we got this expression. Alright, now we will simplify this expression and its calculation. So after simplifying the expression and the calculation, we get this expression of specific humidity. Alright, now using the total pressure of moist air expression, which is this, we will replace PA with P minus PV in the above expression. Alright, so we will replace PA with P minus PV, alright, in this expression, and write the next expression. Alright, right, after plugging in the expression of PA, we get this expression. Alright, now we will plug in the calculated value of PV and given value of P which is equal to 1 bar, which changes from 1 bar to 100 kilopascal using its unit conversion along with their units. All right. So we will plug in the values of PV and P in this expression along with their units. All right. And we'll write the next expression. All right. So after plugging in the values of PV and P, we get this expression. Now we will simplify this expression and its calculation and include the unit, which is kg of water vapor per kg of dry air in the final answer. All right. So we will simplify this expression and its calculation. All right. And then we will include the unit of specific humidity, which is the kg of water vapor per kg of dry air. All right. Because we know that the specific humidity is the ratio of water vapor mass and dry air mass. All right. All right. So after simplifying this expression, we get this expression. All right. Where we cancelled the unit from both the numerator and denominator. All right. And we further simplified this expression's calculation and get this expression. And after further simplifying this calculation, we get the final value of specific humidity of moisture in the room with a unit of kg of water vapor per kg of dry air. All right. Now we will go back to the first page and try to see which option is correct. All right. So from these options, the correct option is option C. All right.